So I don't use C++11 in my day job. This is an evenings and weekends thing for me. I do this in preparation for eventually I'm going to be able to use C++11. So why am I doing a tutorial on R-value references? There should be an expert. And it would be a very different talk if there were an expert up here. I am maybe not uniquely qualified to give a talk on R-value references, but my qualifications are that I have made in the last few months almost every mistake one can make with R-value references. So we're going to be looking at a lot of mistakes. We're going to be looking at the ways that I have found to understand whether I have made a mistake or not. And hopefully I will highlight, here are the mistakes that you can avoid. And when you're writing your code, how to test for, did I make this mistake or not? So I don't know what the future will bring. So I'm hoping this is representative of what C++11 and 14 do. If someone tells me differently, I will probably believe you. I'm leaving a bunch of includes out of my slides. Generally, if you put these includes in with the code that I've written, hopefully it will build. I also, that's not what I wanted. This is what I wanted. This I find to be particularly handy because static assert requires that you give it a quoted argument. And so with this macro, and I think I was just in Tony's speech where he said, don't use macros. So I'm using a macro just to make Tony happy. So this way the assert shows what it was you were asserting. So we're going to talk about why in the heck somebody did this stuff, how to implement it. We're going to talk about universal references, which is a Scott Myers terminology. You will not find that in the standard, and there will be people who will bark at me for using the term. And then overloading with universal references, which is one of the easier places to make mistakes. And then we'll summarize. So we're going to move. Well, why did anybody do this? Why did somebody introduce R-value references? So we're going to improve performance in specific important cases. And almost as a side effect, we're going to allow people to make non-copyable types movable. But that was only again, that was only a secondary issue. It was really about performance. So C++ was released in 1995, and generally Java was slower than C++. Well, let's see, and I've got my numbers wrong. Anyway, Java was slower than C++. Java was faster for passing big objects. Why was that? It really had to do fundamentally with the way Java dealt with data. Any significant sized, anything that was not a value type, there are very few value types in Java. Anything that was an object always went on the heap, and it was reference counted. So here I have an object, and I'm going to return that. So this is my stack. This is intended to represent a scroll. This is the best I can do with PowerPoint. There may be someone who could do better. I'm sure there are people who could do much better with PowerPoint. This is intended to represent a scroll so that my stack can unwind and then wind back up. So here we have a Java object. And on Java, the only thing that you have on the stack is a reference. It's very small, easy to move. So if I want to return an object in Java, all I have to do is create another object here, kick up the reference count here, and then poof, this thing's gone. We decrement the reference count, and it's moved. Yes?
Technically, Java is garbage collected, not reference counted.
Okay, thank you. I'm not a Java person. Thank you. So the statement was Java is garbage collected, not reference counted. Thank you. For that. Thank you. So if we do this in C++, we've got objects on the stack. Now, an object may or may not have part of its appendages sitting on the free store. If something's not, if an object has no contents on the free store or elsewhere, there are places other than the stack, then, the only thing you can do is copy it back up. But if you've got something sitting on the free store, then it'll be over here and you're referring to it from the stack over to the free store. So if you're returning an object, in C++, and here I've kicked the numbers over to 89 because we'll get to the return value optimization in a minute. So if you were prior to the return value optimization, which came about in 1991 initially, and this took a while to percolate into compilers. So we're going to have this local object, and we have to copy all parts of it up one level. We have to have unique copies. So now that we've got that unique copy, our scroll rolls up, the destructors run, everything's gone. But we had to copy a bunch of junk. Well, it wasn't junk. It was stuff that we had to have. We had to copy a bunch of stuff. And that's slower. Now, like I said, starting in 1991, the return value optimization was introduced. And what was interesting about the return value optimization is that you didn't even have to build this thing locally at all. You don't have to build whatever you're returning. You don't build that in your own local part of the stack. Somebody upstairs, when they said you're going to return this, they handed you a place where you can build this thing. And you build it in place where it will be returned. There are no moves. There are no copies. It's just where it needs to be. So this is cool. But it doesn't work all the time. Specifically, let's say that I have two vectors and I'm passing a condition so that at the point when this code's executing, we don't know which of those two guys are going to be returned, either VA or VB. Then the semantics of construction don't allow me to say, oh, well, I'm going to guess that one of these things is more likely to be upstairs. So I'm going to construct it up there. Oh, no, that wasn't the right one. I'm going to run its destructor and then substitute this other one. That's not allowed. So we have to build them locally and then copy them up. It's very silent. OK, I guess I won't worry about it. So we have similar kinds of problems with vector pushback. I've got, this is my vector, and it has its local, not all objects have a part out on the free store. But let's just talk about string as a favorite example. At least I think strings are ubiquitous. They're all over the place. So they're a good thing to talk about. So here we are. We've got a vector of strings. Our vector is full. And we've got this stuff sitting over on the free store that's all referenced by these strings. And we're going to do another push, or we're going to push one more object in. The vector's full. So we've got to make a new chunk of memory for the vector. So we're going to do that. Well, when we did that in 98, not only did we need to copy all this stuff over, but we had to copy all of these as well. And we have to copy this over to here. And once we've done all that copying, then we can wipe away the old one. Okay? So there were folks on the standards committee who were really worried about this performance stuff, and that, that was good. We appreciate that. So the first paper was September 2002, Howard Hinnant, Peter Dimov, Dave Abrams. These are some of the brightest folks I've ever met. At least I've met two of them. And Peter is responsible for a shared pointer. So, smart folks. And there was a lot of work that went into this. There were a lot of papers. So the first paper, where it proposed language support to identify temporaries. It proposed a means to explicitly treat non-temporaries as temporaries. And it introduced some terminology, an R-value reference, and move. So when we move, so we've seen the old case. Let's look at the new case. So here we are with our stack. We've got our object down here. We've got some stuff on the free store. What we're going to do is we're going to take the things over here. We're going to remove the references from here. We're going to create this object up here, have it have the references. There's no garbage collection, no reference counting. This thing is now decoupled from the stuff over here on the free store. It's basically in kind of a zombie state. And now the stack's going to scroll up. It's a catchy tune. So we've got the same kind of thing with the vector. We're going to do our vector pushback. So this time, instead of creating copies, we're going to steal all that storage from this guy. And we don't have to do any extra creation over here in the free store. We're not going out to allocate memory. We're not, this is a huge win.
So just a question?
Yes, please.
Why isn't storage 5A?
Well, so it depends, that depends. That depends on whether the pushback, if one were moving from object 5A, then yeah, you can steal this storage. But we don't know whether, in this particular case, I'm not asserting that when they did that pushback, they did a pushback with a move. So in general, we're not allowed to destroy the contents of the thing that was pushed back unless we know that it can really evaporate. So a finger trap, a MooCan?
No, I'll take a finger trap.
Oh, you'll take a finger trap. All right. The finger traps are lots of amusement. So one of the things you've seen is that something that can actually implement a move, you have to have state stored outside the object. So if your object is a tight thing and all the data is right there, move doesn't do you any good. But if you've got something that the object holds that sits on the free store, or if it's some sort of an OS object, so it's not on the stack, it's living somewhere else, it's outside of your contiguous object. So if you've got that, and you have to have a valid move from state, and we'll talk about what valid consists of. The rules for standard types that are movable are more constrained than they are for user types. And I have some opinions about what makes a good type. And maybe I'm not qualified to have those opinions because they're actually in conflict with what Sean Parent thinks. And he's a way better authority than I am. but I'll go ahead and share my opinions, and you can take them for what they're worth. But you have to have some sort of a valid move from state, because the destructor will run on the move from object. And so the fact to me that the destructor is going to run on it, that indicates that it's still some kind of an object. It's not a partial object. It's not less than an object. It's still an object. So the question is, do you want to even be in this room? Do you want to learn how to do this stuff? And really, there are just a few conditions where you need to move enable. So do you move enable if you don't care about performance, because moving is only an optimization. Moving is a faster way to copy. So if you don't care about performance, don't bother with any of this business. Just go ahead and copy. And that's in direct conflict with several of the talks I've heard. But a lot of people who are involved in C++ really do care about performance. So maybe this is silly. But anyway, if you don't care about performance, and so your types can benefit from move if they aggregate movable types, which means there's, like a string has a piece that's out on the free store. Or if you have some sort of external movable state. If you have an object that references the free store, or if you reference the free store yourself directly, either of those, then yeah, move can save you some time. So these are some of the standard types that move. Yes?
If you can go back to that previous slide.
Yeah.
On one of your earlier slides, you actually listed another motivation for move enabling classes, but you didn't talk about it here. That's when either copying would have side effects, but you can avoid those with a move.
Yeah. So.
Or if the type isn't copyable, like OS handles, you don't want two copies of the same thing pointing to the same handle.
Yeah. Okay. Great. So the assertion was there's another reason to do it, which thank you very much. That's an error in the slides, and you get a cow.
Boy, that'll be fun in my life.
This is the bad one though. Could you pass that over? One of my earlier talks, I started throwing things and people got hit. So I'll try to be more careful. These things actually they're hard plastic, so they've got some impact. So the point was that there is another motivation to move enable your classes. If your type doesn't copy, but you want to be able to move it. And thank you very much. And I guess so the focus on the rest of the slides really was we'll slide away from, for the most part, move only types because they're comparatively easy to implement. I didn't worry about it too much, but I think it's an excellent point. So these are types that move in the standard library. And that subset, those are all move only. So what we've already seen is that moving is a euphemism. What we're doing is we're stealing from something. And moving sounds nicer. It doesn't sound like you're doing something nasty. But what you're doing is you're stealing from something and you're leaving it disabled. You're damaging the object. But we think, what we're doing, and I guess another way to look at it is that this is, the reduce, reuse, recycle. Okay, so we're about to send something off to the trash bin of history. So rather than recycle that memory, we're going to reuse parts. So, anyway, I like stealing. It's a little bit more dramatic. But the parts that we're stealing don't move. There's nothing moving. The parts that are stealing are stationary. The address doesn't change. We are changing how the reference goes. But everything stays put. And this was a reiteration of my point earlier. If you have an object where it has no references to the free store, no references to anything outside of itself. You can't move it. All you can do is copy it. So once you say, gee, I want to be able to do this stuff, what can you move from? So you want to avoid breaking old programs. But we still want the greater speed. So if you have an old program, what can you steal from without hurting the program? Well, you know, most objects, anything that somebody has a reference to, if you have this thing with a name in your hand, and somebody steals the parts out of it, all of a sudden it's not going to behave right, and your program's going to be broken. So what category of things can we steal from? Those are temporaries. Temporaries are interesting because we usually don't even get to think about them. The compiler invents them for us and pushes them around, and then eventually from operations on temporaries, things up getting pushed into values that we can operate on. Once it has a name, then you as a programmer, you can go thrash around with this named thing. But a temporary, you can't do it. That's all up to the compiler. So what's a temporary? Anything that isn't an L value. And I looked through, I didn't spend a lot of time searching through the standard, but any place I found a description in the standard of what an L value is, I couldn't make any sense out of it. Now, that's not that unusual for the standard. The standard's hard to read. But I did find this description that really makes a lot of sense to me, and I think is pretty close to what the standard intends. So an L value is an expression that refers to a memory location, so it's somewhere in memory, either on the stack or free store or something like that, and it allows us to take the address of that memory location with the ampersand, or the AND operator. And so anything that doesn't do that is an R value. So anything that we can't get to, that's an R value. So let's look at some stuff that's R values. So up here, these are L values. Because I've got a string named A, I can go, beat that one up. I've got a string named B, I can go beat that one up. Give me a B, I've got that B. But if I do this, there are a bunch of temporaries being constructed there. You don't get to see them, but the compiler is building them for you. And then eventually, as a result of the intermediate temporaries, something gets popped into ABC. ABC is an L value. If you construct something in place, so here I've got a function that takes a string, and I pass it a char star. So inside that, there's a string. I don't see that. That's a temporary being built. Okay. Do you want a finger trap? The statement was this won't compile on GCC. You want a glider? All right. So I
throw that.
yeah, but it won't go to the right place. I guess I'm a little puzzled that it won't compile on GCC because it
compiles on Windows, but it won't compile.
Okay, that's okay. So I'm using GCC on Windows.
Windows cheats and will make that string object that it can then take a reference to.
Yeah.
But GCC won't.
No, that would be true if there was no const.
Yeah.
Visual C++ allows it to work without the const, but it'll always work with the const reference.
GCC work with the const.
Should. It's standard creation.
Okay, we'll let you keep the glider anyway. Who out of that particular discussion, who else gets a? Okay. So there was a discussion about whether this would compile or not on GCC, and I don't know that we came to a conclusion. It did. I did my best to test all of this code on GCC 4.8.2. So at least for me, it did compile on Windows once. So if a function returns an object, and we'll get to that in just a second, then that object, that's an R value. So an object type returned by a function is an R value. So here we've got two functions. GetInt returns an int, a 2. Int is an object. GetIntRef, we're returning an int reference. That's not returning an object. So the returned int ref, that's not an R value. That's an L value. This is a picture I got from Howard Hinnant that shows all of the things that are object types. And in particular, reference, function, and void are not object types. So none of those will be R values. So now that we're going to do this stuff, the reason we're talking about R values is we're going to steal from them, because this is getting back to what kinds of things can you go mangle without destroying the program. So we're gonna try to find a way to get a hold of those R values. And so we're adding a new type called the R value reference, and it's got 2 ampersands. And we still have the same old C++ 98 reference, a single ampersand. That's now called an L value reference. If you call it a reference, people will probably get it. But in terms of the standard, you've got R value references and L value references, and all that does is how many ampersands have you got? And what we're going to do with those is we're going to do overloading in order to distinguish between the thing that's getting passed in, is that an R value or is it an L value? Used for overloading. So if an R value is coming in, an R value will prefer binding to a double ampersand, but it will also bind to a const L value. But L values will never bind to a double ampersand. So if you don't add any double ampersands to your interfaces, everything will still work. Everything will behave the same as it did before. You just won't get the speed improvements. That's all. So again, you can almost afford to ignore all this stuff if you're not worried about the speed improvements. So when you're setting up your interface, you want to make sure that your ampersands or your double ampersand, your R value reference, is not const, because you're going to steal from it. Make sense? We're getting past something. I'm putting you all to sleep. I'm sorry.
So what does a const R value reference conceptually mean then?
It means that it's an R value reference and you're not going to be able to do the work you want to do. Because if it's const, then you can't steal from it. So you've got this R value reference in your hand, and all you can do is look at it and say, that's a lovely R value reference. But as soon as it's non-const, then you can say, ha, now I can turn it into a zombie, which is what we all want to do anyway.
Is it allowed to make a const?
Yes. Yes. There's nothing in the standard that says you must declare, the double ampersand cannot be const. So you can declare it as const. It just won't do you any good. Kind of pointless. So this is a heuristic. if you see a piece of code where somebody's using the double ampersand just sitting out inside of a function body, then that's almost certainly something that's wrong. It may work. We'll compile and link and all that good stuff. But it's probably the wrong thing to be doing. For one thing, it's misleading. It's like when you look at that, you get puzzled. What are they trying to accomplish? So, generally, don't do this. And if you come up with a good reason to do it, because I'm not going to say that in the vast landscape of C++ that there's never a motivation to do this. That would be an error on my part because the landscape is big. But everything that I found, I am a noob, but I have talked with other folks who are not noobs, and this is not a bad guideline. So if you see a double ampersand sitting someplace other than in a function signature or in a cast, and you'd like to not see it in a cast, we'll talk about that later, that's probably an error.
Excuse me?
Yes?
I've seen in some other talks slides people using double ampersands in range-based for loops, auto, double ampersand, something.
Okay.
Or something, and I looked at that and thought, I have to read up.
Okay,
Work out
so
what that means.
yeah, and thank you. No, I can't.
Okay.
Thank you very much. So I have just been corrected on the previous slide. This gentleman who gets a cow.
Thank you.
So a reason that you might want to do that, let's say you had, a container of things, and you
works.
wanted to
Did you pass that back?
move from all of them. They're no longer going to be used. Then binding the loop local variable by an R value ref so that you can steal from them might be a reasonable thing to do.
Okay, so let me repeat what the gentleman said, that he's been to talks where he saw an auto double ampersand where in a for loop, and somehow someone was doing something useful with that, and it probably had to do with generating R value references or how that binding was happening, and the person who had that for loop was more of an expert than I am. So I think the term suspect is not bad, but what you're saying is that there are probably legitimate uses for it. And just for a heads up, that you don't want to get too comfortable with saying that the double ampersand is always an R value reference. And we'll get to more details on that later. So part of what the standard wanted to do was, in order to get the vector stuff to work, the vector stuff, the things that we're moving from, they're not R values. They're actually, if you go back to that picture I had a while ago where we have this vector, we're going to do the pushback, all those things that are sitting in the vector, they're not R values. They're real honest to goodness values. L values. They have names, they have a place. We want to steal from them anyway. We're going to be, we know that eventually that entire vector is going to expire. So we're going to go in there, we're going to say, I'm forecasting that this stuff is eventually going to become a set of zombies and then I'm going to nuke them. So we need to find a way to turn those guys into R values so that we can do the nuking. So the way you move from an L value is you do a static cast to an R value reference. And it looks like this. And that would be incredibly ugly to scatter all over your code. So the way you want to do it is like this. Call standard move. There is unless you're writing the standard library. And there are people who, probably nobody in this room, although anyway, C++ now is the wrong place to say that because there are a lot of people here who write the standard library. So if you're writing the standard library, then you have great reasons to be writing that kind of stuff. If you're not writing the standard library, use what the standard library provides. It's shorter, it's easier to read, it shows your intent. Standard move moves nothing. There is nothing that moves. All you're doing is you're turning it into an R-value reference as far as the compiler is concerned. Something else has to do the moving. So if you can, when you make something that's movable, make it no except movable. Swap, if it's got no except moves, swap becomes no except. And it also helps with vector. And vectors get used a lot. So if you can make your move no except, then do that. So getting back to how would we take advantage of some of this stuff? So if you're returning stuff, don't return a const object. So we were talking about what objects are and aren't earlier. So if you're returning an object, don't return it as a const, because then it can't be turned into a zombie. It's going to be returned intact. Nobody can steal from it. And we're actually trying to promote this, being able to steal from stuff. So that isn't to say that you should never return anything const. If you're returning a reference to something, it makes good sense to return it as a const reference. But if you're returning a const reference, then you can't steal from it, and that's probably okay. No problem. Yes?
Is it, like in that case, would it actually be less efficient in C++11 because wouldn't you get RVO there? Or am I?
That depends on what's happening to the thing that's being returned. Yeah, so the question was, would it necessarily be less efficient in C++11 because the return value optimization would take over? And it depends on what it is that you're doing with the thing that's returned. But the return value optimization may help you with that. You've got a cow already, so yeah, well, that's okay. We've got these. So you prefer a finger trap or a glider? We're down to 2 gliders.
I'll get a glider.
Okay, the glider it is. Did you pass that back for me? Thank you. Thank you. So just because I've seen code like this, it's really tempting. You want to be efficient. You want to return that R-value reference. You really want to do that. If it's a local, don't ever return a reference to a local. Does that make sense to everybody? Okay. And to me, this really says it all. The stack giveth and the stack taketh away. Yeah, and another thing that can happen is that people get excited about move and they start saying, I want to move this, any place that I can move, that's a good thing. Isn't necessarily the case. So if you do a standard move on a local, yeah, so here we're returning a string. So this is okay, we're returning an object. But if we do a standard move on this, then what that's going to do is that's going to disable the return value optimization. So you're actually hurting yourself.
What if it's a case like when you said earlier where you can't do the return value optimization because there's some ambiguity?
Yeah, and the compilers are really very good about that. When I was writing test code, so the question was, what about the case where there are two of these objects or more and there's a condition, does it make sense to go ahead and do the standard move at that point? And I was thrashing around with the compiler trying to figure out what this stuff was doing. And at one point I convinced myself that there was a situation where GCC was doing a copy rather than a move. And when I went back to it and tried to recreate that situation, I was completely unable to recreate the situation. I think that was my error. I believe that the compilers that are dealing with move are very good at recognizing the situation that this scope is closing. So here I am. I've got these local objects. They're all zombies. I can do the move from any of them. So if you wonder whether it makes sense to do that move call, then I would suggest that you do a test first. So I think the compilers are very good.
Just to talk on this example, the one place you do want the standard move is if you're returning something that's constructible from a string R value. So if you're actually constructing a return value, then you want to use this neutral, and then you'll call the constructor within your constructing the R value of the string.
I think maybe I should have you come up and speak into the microphone, because I don't think I can repeat that.
Sorry?
I think I should have you come up and speak into my microphone, because I don't think I can repeat what you just said.
Oh, it usually picks up, so you don't have to worry about repeating it too much.
Okay, thanks. So we had, and you get a cow. So we have apparently one case. This one works well. I'm going to send that back. So we have one case where it makes sense to call standard move on the way out. So we've got, why in the heck would we want to do this? What are we going to implement? So there are some, I ended up reducing this into 3 different ways of looking at the problem. The compiler does a lot of move stuff for you. And then there are all those types in the standard library that are movable. And then eventually, sometimes you have to write your own code. You can't just rely on everything that comes from the standard library. So we've got these C++11, or actually C++ special member functions. And so these 2 at the bottom, they're new with C++11. So you have a move constructor, you have move assignment. They're new. And what I'm saying is that the compiler will build these things for you. Sometimes. So here we've got a class. This class has a default constructor, and it doesn't have any other constructor or any of that other stuff. So do I have an assignment operator on this? Boy, I've really put you guys all to sleep. Just if it were C++98, is there an assignment operator in there?
Yep.
Yeah, okay. So there's also a move constructor and a move assignment. Because we can do a static assert. Is no throw move constructible? That's true. The compiler built those things for you. They're invisible. They're not in the source code, but they're present. So this is kind of magic. You can take already existing code, build it with C++11, C++98 code, build it with C++11. And some of it's going to just kind of magically run faster. That seems pretty cool. So in terms of no accept, when the compiler builds these things, what it's doing is it's looking at the contents of the object, of the contained non-static data members. So what it's going to do is it says standard string supports move. So it's doing an introspection on the data types. It says, oh, okay, that's a movable type. Therefore, the thing that contains it is also a movable type. So if everything that's contained is movable, then your type, this class, move1, that also has move semantics. So if all of the non-static data members have no except moves, then the compiler generates a no except move. And it has to look at the move constructor and the move assignment distinctly, because each one of them could be no except true or no except false. So you're going to see a fair amount of test code up here. And the reason for that is that I was struggling with how in the heck do I test this stuff when I was trying to get ready for this. Because what you're doing is you're stealing objects, you're leaving zombies behind. If how do you know whether you've actually done this work? And part of this is motivated because a year ago I wrote what I thought was a correct move constructor. And it turned out I'd implemented copy. It all looked right to me. But I was looking for, this time around, I wanted to be darn sure that I actually got it right. So part of what I'm doing is I'm examining the results of the moved from object. Not here in this case. Yeah, here. Okay. So I'm moving from MC, and I'm going to make sure that MC is empty. So that's the key that I actually successfully moved. Now, at this point, Marshall's going to walk up, and he's actually, after Marshall talked about undefined behavior, and I was sort of shaking in my boots because my slides were all ready. And I was wondering, well, gee, am I relying on undefined behavior? Which was, legitimate thing to worry about. So it turns out I'm not relying on undefined behavior. I'm relying on unspecified behavior. So I am standing on uncertain ground at the point where I'm examining that string that I've stolen from, because the precise state of that string is not specified by the standard. So a lot of these tests, what I'm doing is I'm relying on implementation specific stuff. So you can't just walk up and assume that no matter what the string is, after I steal from it, it'll be empty, because it might not be. But by thinking about string implementations, I can say, well, probably most of the time, this is a legitimate test. But I am relying on unspecified behavior. What I can do is I can call empty. And empty may return true or false. Even though I've stolen from it, it may not say that it's empty. And some of that has to do with the way string works, or many string implementations work. If the string is small, then there's the small string optimization that the body of the string may actually go inside of the string itself. In which case, it's up to the implementation is, when you did that move, it didn't actually move anything. All it could do was a copy. Yes?
Once you've stolen from the original one, and you do it as empty, isn't that like an invalid reference then? Is there anything really there?
So the question was, if you call empty on a string that you've moved from, isn't that an invalid reference?
That's the question.
Yeah, that's the question. And you get a cow. So the answer is no. And that has to do with the way string is specified in the standard. That string will be left in a valid state. So you can call empty. What you can't do is, let's say that you had a string that was, so many characters, and once upon a time you were able to do an array index into that string and suck out a character. Okay. Once you've done the move from that, you can no longer assume you can do that same array index. You kind of have to go back and revisit it. It's like an iterator at that point, that you actually, you can examine it, you can ask it stuff, but its state has changed. So, and that has to do specifically with the people who wrote the standard decided that their types needed to be fairly well behaved when they were moved from. But that's, if you write a movable, something that can be moved from, then you're not necessarily constrained to that rule. Okay, but the standard decided to be nicer. Yeah. Does that make sense? Yes. I'm going to get corrected again. That's good.
It's a little bit question, but so because he asked, is it a valid reference, right? So because the doesn't move says that you still have to have a valid reference when you're done. It's just your object may not be is in an unspecified state, so any of the operations of your object might not work, but it's still a valid reference. I don't know if that's what you asked.
We're not talking about references, actually.
Okay.
We're talking about a move from standard string, which could be an object.
Okay. Do I need to repeat any of that for the? Okay, we're good. Thanks. Let's see.
I just also want to make sure I fully understood. That's all.
Okay. Okay. Yeah. No. So the string's still sitting there. But somebody stole the guts out.
Yeah.
Potentially. If there were no guts to steal, then potentially nothing got affected. And so you'll see in the slides, I try to go to some effort to make my strings long so that I can avoid the small string optimization. That's me weaseling. Okay, I cannot guarantee that for your implementation that will work. John.
I just wanted to point out that if you take the size of the string, you're probably on safe grounds if your string is bigger than that. Take the size of the string object. That we have to do this too.
Yeah.
So we want to make sure our short string optimization is not dominating the whole thing.
Okay, so
take the size of it, you know how long it needs to be, at least.
okay. So John's saying that if you take the size of the string, you're probably safe. Thank you. Yes. Oh, and do you want a glider? We only have one glider left.
No, somebody else gets the glider. I want the cow.
You want the cow? I have to test it.
Last time.
Yeah, that worked.
I'll be using this all day.
So, question?
Yes.
So does the standard make no requirement at all on a moved from object? So if you define your own move
Yeah. So
is there any requirement at all? I mean, if I called explicitly the destructor for that object in the move,
so
obviously the destructor can't run again.
Right.
Is that legal, or
Yeah.
is that?
Yeah. So the question is, does the standard require anything in particular for a moved from object? And so there's one for sure. The for sure is that the destructor has to be able to run. Okay. There's another one that I think is not necessarily a requirement, but is a very, very good idea. And that is, if your object allows assignment, it should be assignable. But I don't know that the compiler or that the standard requires that. So that's just a particularly excellent idea. Yes?
If you're going to put the type into, say, a standard vector, it's a good idea to have it assignable, because otherwise it'll break when you resize or something like that.
To have it what?
Assignable.
Assignable, yeah, okay. So if you're going to put the object into a vector, the statement was finger trap,
Yes,
cow? Okay, finger trap. So if you're going to put the object into something like a standard vector, then having it be assignable is an excellent idea, was the statement. Yes?
Are the move constructors also automatically created for
objects where moving doesn't make sense, like where you don't have any free memory parts, where everything is sitting in the class?
You know, I didn't test that. So the question was, if you have an object that doesn't have anything that's movable, are the move operations still generated for it? I'm not sure I know how I would have tested that. What's that?
You could test it.
Oh, okay. You could do it with this with the.
And the answer, I believe, is yes.
Okay. That
It doesn't matter.
Yeah. So Todd says that yes, it would create it, and the effect would be that it would do the copy. And so, what do you get, Todd?
Oh, I'll take a glider.
Okay. The gliders are gone. Okay, great questions. So the thing about the implicit operations is that they're really easy to lose. So I don't want you to memorize this. I just want this to be scary. So, and thinking only about the move constructor. Okay? So if you had, you created a really simple object and it had a move constructor, as soon as you start adding members to it, this stuff starts to evaporate. Okay? So this implicit stuff, which you can't see in the file anyway, it starts to disappear. And to me, this is particularly problematic because the functions that your object provides, that's your contract. And so whether you can see it in the file or not, people can still call it. It's still part of your contract. This is half of the rules. Here are more rules. These are things that can make your implicit copy constructor or move, your implicit move constructor or move assignment. Well, in particular, we're looking at the move constructor only here. These are things that can make the move constructor disappear. There are corresponding rules that will make the move assignment disappear. So if you're going to rely on an implicit function, you can either guarantee that it's present with a static assert immediately after the declaration of the class. And that way, while you're modifying your class, you can see whether, yeah, I assumed that implicit thing was going to be there, and it disappeared. Or you can explicitly request the default implementation using the equals default.
Or both, right?
Beg pardon?
Or both.
Or both, yes. Both is a great idea. Thank you, John. Yes?
You use the word request. Does that mean that equals default might not generate one?
No, that was a great point. Request is a bad term for that. Cow or finger trap?
Whichever. Cow.
Cow.
So the more thematic.
Oh,
So
this one's a silent cow.
the question I had that related to that was that there were some conditions on the previous slide, like non-trivially copyable members. And if you had that condition, would it generate one and make them copies and move everything else, or would it just say I can't generate it?
It just doesn't generate it. Yeah. So if there's anything in there that isn't movable, it's not movable.
But if you explicitly request the default behavior, do you get a compiler or is it just silently not generated?
The default behavior is to generate a move constructor if it can be trivially generated. If it can't be trivially generated, the default behavior is to not supply one.
Okay.
Yeah.
So if you just say, please do this for me if possible, and it's not possible, then you don't get it.
So it is a request.
No, I think you're right, that if you say equals default on a move,
So if it can't, is it?
I wish I had my compiler here.
If it can't do it, it won't compile.
I believe I experienced
The
that.
reason, this typical reason you use an equals default is either because of your coding convention wants you to just be really explicit, which isn't a bad idea, or you have declared one of the special functions like a constructor that would disable it, and you want to say, actually, I do want it, and it should be the default.
Yeah. Okay. So do you get another finger trap?
I'm sure more people can have questions.
Okay. So I believe that you're, I'm agreeing with you that if you say equals default and it can't generate it, then you'll get a compile error. Now let's see. So where am I? Okay. So what I've got here is a unique pointer. Unique pointers.
Sorry, I just wanted to touch on, I think this is actually a little bit of a gotcha, because if something is copy constructible or copy assignable, it is move assignable and move constructible. So it doesn't necessarily, your static asserts, I don't think necessarily mean that a move constructor has been actually created. It could just mean that the copy constructor is no except. I think that trait will still be true in that case. I'm not sure if it really matters, because if it's a no except copyable, then you're probably all right, and you probably don't need a move, but I just wanted to point that out.
Okay.
Sorry.
That's good. That's good. So anyway, what I've done is I've put a unique pointer in here. A unique pointer is move only. And it sounds like there's an error in the slide. But what I get out of this is that because unique pointer is only movable, it is not copyable, then you, let's see, you can't move construct is true, but copy constructible is false. So
in this case it works.
So in this case it works. Okay. So, but that has to do with unique pointer being the member rather than a string. And we'll test it, and this doesn't compile. There's no copy. So the next thing to do is, well, let's see. Yep, okay. So what I'm going to do is I'm going to say, yeah, I explicitly want this thing. And our static assert works. And we're going to test it. And what happened, because we added this move constructor, we took out our copy constructor. So, and just to be clear, we've gone back to the string example. So with the string example, we could both copy and move. But because we declared one of these guys, this one went, or the copy constructor went away. So there are still risks even when you're explicitly declaring these guys. Now the nice thing is we got this at compile time. If you're building a library, then you're more clever than all this. But at least when you called it, it didn't fail silently. So explicitly declaring the move constructor deleted the implicit copy constructor. If you're going to default or delete any of the special member functions, then it probably makes sense to do all of them. So do the whole set. And at least when you talk with Howard Hinnett, Howard will suggest that you just go ahead and do 6 static asserts after pretty much every class. And depends on how good you are. But there's no runtime cost, is the nice thing about that. So you've got all these traits, you can use them. There are no-throw and without no-throw versions of all of these traits. So now that we've got all of them, they all work. So if we've got movable types, So I've got my string, which I didn't, yeah, okay. So the string fell off the bottom of the slide, but I've still got a string, my S underscore. So here I've got this R value reference, and I'm going to move that R value reference into my string, my local string. I gave it away. There is a bug here, and I'm sure a number of the folks in this room know what that bug is. Somebody shout it out, and then I can give you a finger trap.
Copying it.
Yeah, so what's the problem here?
That's doing a copy.
Yeah. So actually, I've still got cows left. You want a cow for that? Yeah, sure.
Sure.
This is a functional cow. Send that cow back. So this is a copy. That's not a move. Why is that? So again, what we're doing is we're looking at the moved from object, and that failed. So the problem is that this, even though it's an R value reference, that's what we would call it. It's not an R value reference. That's an L value. It's got a name. I can refer to that. I can go pick up that memory in RHS. So even though it says move, with a double ampersand, that's an L value. You have to move from it. So if you go back many slides and we talked about what's an L value, this thing with a name, that's an L value. So to me, we're staring at the biggest user trap in R value references, period. That my general assumptions with things in C++ is when I see the name of what I'm looking at, I can't do this with auto anymore, but if I've got something other than an auto and I'm looking at it and basically it's telling me what it is, that's not the case. This is not an R value. This is an L value. You have to move it. I probably beat that horse hard enough. But this was one of the first things that bit me, and it's really easy to mess up. So when you're moving, when you're inside of this signature, you have to call standard move if you want it to behave right. Otherwise, you get a bug. And I'm going to get corrected again.
So
That's good.
The slide, the thing is, you're not passing RHS into that constructor. You're passing its member,
Yeah.
S underscore. So it doesn't matter that RHS is an R value, whether it's an R value reference or an L value.
Yeah.
Doesn't matter if S underscore is an R value reference or an L value.
That's actually an excellent point and a good correction. Thank you. That the statement was that it's the .s is what's actually getting passed. What I will say is that if it weren't the .s, if it were the RHS that were being passed into the constructor, the same thing would be true. But thank you for the correction. And let's see. Do you have both a cow, or do you have a cow yet?
I have a cow.
You have a cow. Do you have a finger trap?
I don't have a finger trap.
Okay. Well, you get the finger trap. So, thank you. So, but you do have to move from it. So, always use that. Always use standard move. There is no runtime cost to the move. It's just casting. So there are situations, like if you have an int, you don't necessarily need to call move, but that's okay. It never hurts. There's never any harm to calling move in this situation where you're moving. So always call standard move. Yeah. So here we are. We've basically fixed the bug. And the test passes. So in terms of move assignment, so this is a bad test for move assignment with string in particular. Our string is again, our sort of the thing that we're carrying around. So I'm sure someone's going to tell me why. I've put you all to sleep again. So it is allowed that the string move assignment may be implemented with swap. So we're going to assume that the move from object will be destroyed soon, because what we're doing is we're saying that thing's a zombie. That's about to go away. So we can do more than just turn it into a zombie. We can pile our garbage onto it. So in the case of assignment, you've got a string sitting here in your hand that you don't want anymore. You want the one from the other side. So rather than unloading that stuff back into the free store, you can just do a swap. And eventually, when that R value reference, when its destructor runs, that memory will eventually go back into the free store. So that's a way to implement move assignment. So testing move from objects is dubious. The destructor is guaranteed to work. I think, again, I don't think this is required by the standard, but you should certainly, anything that comes out of the standard will do this. And you're really smart you're avoiding a lot of trouble for yourself if you do this.
Because that swap doesn't work. Is that right? With that, if you don't provide that.
Swap doesn't work. Right. Thank you, Ray. So, cow?
Sure.
I think we only have one functional cow left. And everything else is implementation dependent. But at least in my experience, and I haven't heard anyone disagree with me yet, there are really only two ways of looking at move. You can either instrument a class so that you can say, I am calling this function and print something out or have some kind of a side effect. You can instrument the class, or you can examine the thing that was moved from. Todd's got another suggestion. Go ahead.
I forget who it was at the back.
Yeah.
Said he was right. Having a copy constructor that accepts a const whatever ref is sufficient to be considered move constructible. If that copy constructor is no accept, then you are no accept move constructible.
Okay. Did that pick up on the? Okay. So I won't repeat that. Thank you.
So yeah, I'm not sure how you actually.
Yeah, I don't. So John.
These horrible things called allocators, and if you just measure directly what memory's going on, it's all done.
Okay. Okay. So John says there's yet one more way to look at it, and you can look.
The only one.
Okay. So John says that. Yeah. To actually look at the memory through using the allocator.
And it's actually really easy because we have a notion of a test allocator that lives in every test driver. You just plug it in, and it'll let you know what the memory usage is. It's done. It's done right out of the box.
Oh, okay. Okay.
It's a good way to do it.
Okay. Well, thank you, John. Let's see. You have a.
Oh, a finger thing.
Yeah.
Thank you.
Cheers.
So John says, be more clever than I was. Put in a test allocator. Yes.
Are there any code samples floating around showing implementing what John was saying?
Yes.
He didn't let me answer. Kevin's right. Yes, there is one, and in fact, he could tell you where to go look to see this in practice. All the test drivers, all the code.
If you're interested, just find me after the talk.
Okay. Thank you. 15 minutes. I got to move faster. So generally, if you're going to start implementing stuff by hand, avoid loose pointers. put free store objects or keep track of free store objects using unique pointer, and then let unique pointer do the moving. So here, because we've got a pointer to a string, we can actually use the default implementation for the move constructor and the move assignment operator. We have to do more work here, but that's work we had to do anyway to allow for copy. And if you really insist on doing this stuff, and honestly, if you're dealing with something other than the free store, if you're dealing with an OS object, you have to do something equivalent to that. You don't get to call delete, but you have to call some OS function to say, I'm releasing this thing. So you have to do this kind of work.
Aren't you repeating the copy issue here?
I beg your pardon?
Aren't you repeating the copying here? Because you're not saying standard move. It's counting the pointer.
It's a pointer.
Yeah. You don't need to remove it.
Okay.
Right.
Yeah. So if you really end up getting down to the base level, this is what we're doing. We've got to do two things. We've got to take stuff from the right-hand side, and then we have to tell the right-hand side that it's now empty. Let's talk about move assignment to self. So,
Go back to that.
yes.
You just demonstrated why people recommend using swap to do that. Because you didn't free what P pointed to before copying P from the other object. Oh, that's in your constructor.
Yeah, this is in my constructor. But yes, I will agree with you that this is.
Applies the assignment operator.
Yeah. So this is in terms of memory, this is not recommended. Use unique pointer. Unique pointer does the right thing. It's really easy to forget to delete stuff. So finger trap. Okay. I'm going backwards. Let's not go backwards. So move assignment to self. In general, move assignment to self from the standard library may leave you with an empty object. So it's not guaranteed to be a no-op. It is guaranteed to be, crumb. Okay, so standard string, if you look at the standard string is so ubiquitous that they said, yeah, if you do move assignment to self, that is a no-op on string. But on pretty much anything else, the behavior is not guaranteed. On unique pointer in GCC 4.8.2, it is a no-op, at least in Windows. I don't know anywhere else. But move assignment to self. Move assignment is supposed to be an optimization, and so if you think about that test, so I personally like doing the test because I like to know what's going on. But if you think about doing this test inside of, here I am, I've got a vector of 10,000 things. Do I want to do that test for self 10,000 times when what I'm doing is an optimization? You may not want that. You may choose to have move assignment to self leave you with an empty object. That's a valid approach as far as the standard is concerned, I believe. John's looking at me sideways. I'm nervous now. Okay. So if we're going to talk about non-free store moves, so some sort of an OS kind of a thing, so I'm going to prefer that, and I'm the novice, but I'll have a bias anyway and then take it for what it's worth. I think that swap-like behavior is not clever in this case, because if whatever kind of file system object you've got, whether it's a file handle or whatever else, if you do the swap, then the point where the destruction runs is outside of your control. you're deferring that destructor for some indefinite amount of time. Howard Hinton would say it's not indefinite. We know that when the scope of that object ends, that the destructor will run. But you're no longer, here in your code. You're leaving it to someone else's code that eventually you're trusting them to run the destructor. So I think it makes sense to not do the swap thing if you're dealing with non-freestore. Now, we've been talking about assignment and constructors. How about setters? Yeah, okay. And I ended up going with a multi-argument or a constructor from not the same thing. So I've got a constructor from a string for my file. And yeah, this works great. This is not a bad thing to do. Now, how about if I've got a multi-argument constructor? So here I've got a path and a file. I'm going to pass in two strings. Well, wouldn't it be cool to be able to do a move with that? Well, what happens if only one of them is an R value? Well, or it could be the other one, or both of them. So this is just two arguments, and we've now gone all the way to having 4 constructors. This doesn't scale. And that's a setup for talking about universal references and perfect forwarding. And I think we should all just bask in the glow of the photo for a minute, because these are perfect cows. So tuple has a constructor that takes n arguments. How many things can you put in a tuple? And that probably has something to do with how many angels can dance on the head of a pin. So, and any of those arguments may be R values. What do we do? So the folks who are working on move semantics said, we're going to make a special rule. We're going to make this thing, if you have a template that's locally deduced and contains an R value reference with no const and no volatile in front of this one's really special. So there was this forewarning a long time ago. Okay, we've just walked into it. This is it. So this thing, learn to recognize this. Scott Myers calls this use of double ampersand a universal reference. And it binds to almost anything. So when you recognize this, you have to make sure there is no const or volatile in that T and T must be locally deduced. That means that if you're, let's say you've got a vector, the vector is of a type, then as long as that type is what you're referring to in your method, that's not locally deduced because the vector determined that type. Did that make any sense to anybody? I put you to sleep again. That's all right.
Say again.
So I've got a vector of T, and I've got 5 minutes. I've got a vector of T. If I use T in a method of that vector, then T is not locally deduced in that method. And that's not a universal reference. It's only if that method, now if I don't use T, but I use P or Q, something that isn't determined by the type of the vector, then it's free to be able to adjust. And in that case, this is a universal reference. So universal reference type decodes, since we've only got 5 minutes, I'm going to slip just past this stuff because this was interesting to me, but I think it's not that important for people to know. What I'm doing is I'm building the perfect forwarding stuff. And all I want to say is use perfect forward. Don't build stuff yourself. So here, if I have a universal reference, So here we've got a locally deduced type P and a locally deduced type F. And I've got those in here. I want to call standard forward on that. I don't want to call move, I want to call standard forward. And now those 4 distinct constructors turned into a single templated constructor. And let's test it. And it worked. So Howard Hinnant saw that and immediately said, that's not a very good templated constructor. You really should guard it. So his recommendation is to use the enable if, because we really only want to accept arguments that will convert into a string. Okay? I don't know what happened there. Or did I just run? That's 6 o'clock. Let's see. Okay. Huh. There's some magic button there. So, we've seen that. So there are things that you can't perfectly forward. For the most part, most of us ordinary programmers don't care. I shouldn't say us, just me. Ordinary programmers don't care about most of these. Don't move from a universal reference. Use forward. The problem is that a non-const L value, if you use move inside of there, a non-const L value will be moved from. So you definitely want to call forward. And so it's really important to be able to identify the difference between a universal reference. Again, that won't show up in the standard. In the standard, they call that an R-value reference. I think Scott Myers is really smart, saying these are really 2 different kinds of animals. Let's give them different names. Okay. So we're going to do some overloading with universal references. This is me walking through making as many mistakes as possible so that hopefully we can end up someplace useful. So I've got this class that I was thrashing about with, and I wasn't paying very close attention. And this is forwarding because I've got this locally deduced S. And so, or particularly here, I've got this locally deduced S. Here are my double ampersands. And I've got this move. But I wasn't thinking about universal references. I was thinking about, I'm trying to do R-value references. And this one's particularly bad because this is a runtime failure. What we've got is a non-const string, and we're running this constructor with it, and we've just emptied that string. We turned that string into a zombie because we called move inside of a universal reference. So the cure for that is to recognize universal references and always use standard forward when you see them. So here's the next bug. We recognize the error of our ways. We said, oh, this is a universal reference. It binds to anything. And so I've got my 2 constructors here, my R-value reference move constructor, my copy constructor, and I've got my cool special constructor that does the forwarding so that I can forward strings. This also has a bug because this universal reference will bind to anything. This one's not as bad. So here, I've got a non-const bad move 2, and I'm passing that in here. It's going to go to the wrong constructor. it's going to go to the one that we weren't thinking about. We expected it to go here to this const L value, but it doesn't bind here because it's not const. It binds here. So how do we fix that? Universal references bind to anything that other overloads don't explicitly specify. So Scott Myers suggests avoid overloads on universal references. Sometimes you can't. So here what I've done is I've said, all right, well, by gum, what I'm going to do is I'm going to do all kinds of template heroics. I'm going to do tag dispatch. And I'm going to look at the type that got passed in. And if the type is my type, let's see if I can dig it out of here. There I am, is same, bad move. And I'm removing the constant and volatile. And I'm removing references. Is this my type? And if it is my type, then I'm going to call one of these two. And if it's not my type, I'm going to call this one. All kinds of heroics here. And what I've done to make sure that these two guys don't get called is I've deleted them. This doesn't work either. Because when you delete a method, you can't refer to it at all. You didn't just say, compiler, please don't implement this for me. You said, this cannot exist in any form. You may not refer to a deleted function. A program that refers to a deleted function implicitly or explicitly, other than to declare it, is ill-formed. So that's not a way out. So we have to implement these guys. We still have this one. So we've got 3 private constructors. We've got 3 public constructors, one of which with this terrifying template stuff going on. So, but this passes my test. Once I've gone to this level, it passes my test. Showed this to one of my reviewers. He said, there's a better way. Yeah, and he's a smart guy. So if you do, in this particular case, because our class, OKMove, does not have a conversion to string operator, we can do this. We can say, if what's being passed in is a string, then do this forwarding operation. Otherwise, do this. So this is one of those cases where tag dispatch is less good than the enable if trick. How badly do you want that universal reference overload? You decide. So, guidance. Don't return const objects because that defeats moving. Use and only in signatures, although I think that's not necessarily valid suggestion now. Okay, there are apparently cases where that's useful. Don't use const in double and signatures because you want to be able to steal from that thing. Prefer, when you can do it, prefer no except because you get better results. Don't standard move return values. It disables the return value optimization. Use static asserts to validate your special member functions. Learn to recognize the difference between universal references and ordinary R-value references. Use standard move with R-value references, forward with universal references. Be careful when you're overloading on universal references and test your work. Probably with test allocators. We're 5 minutes over time, but I think it's worth making the point that move semantics is not a cure-all. And this article by Eric Niebler came up in, I think, at least one of the other talks earlier. This is really interesting, using stateful objects for returning information. And these are my sources, and the slides will be available. Thanks.